So this video is about the test for goodness of fit. So the distribution that we're going to use for this one is the chi-square. And remember what the shape of that distribution is, right? Well, it's kind of like that. It can be a bunch of different things depending on your degrees of freedom. So this will be based on degrees of freedom. And we'll talk about how to figure that out for these situations. So what we're going to do is we're going to test whether a given distribution, not this kind, a given situation matches what we expect. So to do these tests, we're going to need observed values and expected values. So observed, what you actually see. Expected, what would you expect based on, the hypotheses. So we are going to be computing the expected values, right? And because, it's all set up for us now, I'm going to have to tell you what the observed values are. If you were running your own experiment, you could predict what you would expect. You could go out and then do your observation, see if they match. Okay, so, and here's a note. If your situation doesn't give expected value percentages, or they don't tell you what the expected numbers are going to be, but they might say something like equally distributed. So if that's the wording you see, then what you'll do is just take the total of how many you have, the total n, and divide it up evenly. So expected values, we're going to compute these. And observed values will be given, in the context of our given questions here. So let's practice finding those expected values, because sometimes that can be a challenge. So M&M's used to claim, they've taken all of their proportions off, used to claim that they had 15% brown, 20% orange, 25% green, and 25% red. The rest are blue. So if you had a bag that contained 80 M&M's, how many of each type would you expect? So let's think about the different categories that we're going to have here, It's going to be the different colors of M&M. So I'm just going to do a little table. So brown, orange, green, red, blue. And we have 80 M&Ms to share, So if M&Ms is saying that this is how they're apportioned, then I would expect 15% of the 80 to be brown. So I would just grab my calculator and do 15%, remember to make it a decimal, times 80. So 12, we would expect 12. So this is going to be my expected value. For orange, would expect 20% of the 80. So is that 16? 25% would be green, so 0.25 times 80, 20, and red is the same amount. Now here's a clue about degrees of freedom. It tells me that the rest are blue. So how many are left to give to the blue column? So you could either add up your percents and take it away from 100, or you can add up the total number of M&Ms that we've accounted for and take that away from 80. And 12. So those are your expected values. Okay, next one. A meal delivery service wants to determine if deliveries are equally distributed throughout the week. It delivers 500 meals per week. What are the expected values? So throughout the week, so if it's 500 total for the week, if they're equally distributed, that would mean that each of the 7 days would get the same number. So for this one, we'd take 500 and divide it by 7. And now we're going to have to round. So I'm going to go with 71.4. And that's going to be the same number for all of them because, if they're equal, that would mean that each expected amount would be the same. Okay. Blood types, 4% AB, 10% B, 42% A, and 44% O. So let's say we had a class of 30 students. How many of each type would I expect to have? You are more than welcome to pause, write down your answers, come back and check. Okay, so 4%, so 0.04 times 30 is 1.2. And 10% of the 30, that'll be 3. And 42% of the 30, that'll be 12.6. And finally, 44% of the 30 will be 13.2. Okay. How'd you do? Cool. So here's another equally distributed. So, but this time it says 5-day week. So Monday, Tuesday, Wednesday, Thursday, Friday. And we're going to split 320 patients up equally distributed, right? So you're going to take that 320 and divide it evenly into the 5 categories, so 64. So these are the expected. This is what we would have to calculate before we could run our test. Then, right, maybe we would go out and actually see, we would, right, check with the clinic, and did we actually see 64 people on each day? And probably not exactly 64, but was it close enough to 64 for each day? Okay, so our hypotheses. So these are called goodness of fit. How good does our observation fit what we expect? Okay, so our null hypothesis, there is no preference, or you can say that the data fits what's expected. So what we get is what we expected. And the alternative say is that there is a preference, or that the data does not fit what we would expect. Okay. So in terms of the variable chi-square, the parameter chi-square, right, chi-square equals 0, right? The closer chi-square is to 0, the more there isn't a preference. Okay, the more that our expected and our observed match up. And remember, chi-squares have to be positive. So symbolically, our alternative is going to be that chi-square is greater than 0. And now we just have to know, is it far enough away from 0 to be significant? So always right tail test, there we go. And then we have some assumptions. So for this goodness of fit test, the data are from a random sample, and this one's kind of tough. The expected frequency, so the expected values for each category, has to be greater than or equal to 5. If you don't have option 2, then you have to collapse some categories. So for instance, as I look up at A through D above, my blood type example wouldn't work because I have 2 expected values that are less than 5. And even if I combined type AB and type B together, I still don't get past 5. So I would either need to up my N value. Well, that's probably what I would have to do. I would have to up my N value. Okay, and we can do these using the traditional method. We'd get our critical values from the chi-square table, or the p-value method. So if we're going to go traditional, I'll tell you what the test value formula is. So your test value chi-square, so remember our sigma for sum up, and then it's observed minus expected squared divided by expected. And then the degrees of freedom, because remember the chi-square comes from degrees of freedom, it's the number of categories minus 1. So I'm going to show you, I alluded to this back here on the M&M's example when we got to that 12. So for the M&M's example, the degrees of freedom would be, so 1, 2, 3, 4, there are 5 categories. So 5 minus 1 is 4. So this, the degrees of freedom, would be 4. And the reason why is that once 4 of the cells are filled in, so once I knew those 4 numbers, the 12, 16, 20, 20, there was only one number that could possibly go in that last column because they have to add up to 80. Kind of the same here with the blood types, right? Once I knew the first three values, I did not have to multiply 44% times 30 to get the number of O's. I could have added up these students who had already accounted for and taken that away from the 30, and that would equal the 13.2. It's a little different when we rounded up here for the 71.4. That might not add up to exactly 500 because we rounded at some point, but that's how we get to the degrees of freedom. So I am probably going to do p-value method, but we'll see how that looks. So let's go ahead and do a couple of examples. So from a survey that we did, I got the following information about people's political party preferences. So I am curious if my students are equally divided among the categories, and we're going to test at alpha equals 0.05. Okay, so let's see. Let's go ahead and find our expected values. So the first thing I need is I've got that equally divided, equally distributed. So that means I need to share all of these students. Well, I need to know how many all is. So let's go ahead and add up those numbers. Get a total. So 52 total students, and then I have 4 categories, so we'll divide by 4. So that's 13. I would expect if they're equally distributed that I would have 13 of each category. Now none of them is exactly 13, but are they all close enough to 13, right, to be valid? So let's go ahead. So our null hypothesis, chi-square equals 0, or in words, the students are equally distributed, what we expect. So remember, if they are exactly right, if these were all 13s, then think about that formula for the test value, observed minus expected. Those would all be 0, right, if it exactly matched. So then chi-square greater than 0, students not equally distributed. So how can we do this well, let's go ahead and write out the test value computation. I'm probably not going to do it this way because my calculator is more than happy to do some of this for us, but well, we'll see. Okay, so chi-square test value. So observed, I have to do 4 of these. So observed minus expected squared divided by expected. So that was the Democrats. So 17 observed minus the 13 expected squared divided by the 13 expected. And then, right, we sum that up. So now we do the Republicans. So 12 minus 13 squared divided by 13 plus 9 minus 13 squared over 13, and one more, plus 14 minus 13 squared over 13. So we could just sit and punch that out on our calculator. Okay, let's do it. I hear you. Okay, here we go. I'm going to do some of the arithmetic on the top in my head first, just so I don't have a whole bunch of stuff. So 17 minus 13 is 4, squared is 16. So I've got 16 divided by 13 plus negative 1 squared over 13, so 1/13 plus, there's another 16/13 and another 1/13. So my test value, my chi-square test value is 2.615. So I guess we're doing both traditional and p-value method. So how am I going to find the critical value? So it's on the chi-square distribution, so go ahead and grab that. Alpha's 0.05, and we're a right-tailed test. So I want to go to the right and cut off the right 5%. And I also need to know my degrees of freedom. So I have 4 categories. So my degrees of freedom will be 3. So remember your table setup to go to the right. So I'm going to find 0.05 and come down to the 3. And it looks like it's 7.815. My test value is less than that, so that would be over right in the meat. This is our do not reject. Versus being in the tail is our reject. So our critical value, 7.815. I'm just going to fill everything in because you just don't know how the question's going to come. Let's go ahead and do our decision and summary, and then I'll show you on the calculator how to get that p-value. So decision, we're going to not reject, so do not reject. The null hypothesis. So there's not enough evidence. To equally distributed. Okay, so my claim is the alternative that they are equally distributed. So that we're not going to reject that. So there's not enough evidence to reject the claim. The students are equally distributed. Okay, so how do I have my calculator do all of that other work for me? So we go to our stat menu, of course, and we get us some lists, and we're going to go ahead and I'll grab my L1 and clear it, and my L2 and clear it, and we're going to put in all of your observed in one column. And maybe you want to make a note of where you put those. Let's see, I'll do it over here. So L1, and then go over to column 2, and we're going to put in our expected, and those are all 13s. And then stat test, and it's down at the bottom, so I'm going to go up from the bottom. And there, chi-square GOF, goodness of fit, right? So TI is all ready for us. So tell it where you put your values. Mine's all set up for L1 and L2. Remember, those are down on your number keys. So the blue key and then the number we'll put in the correct list. Degrees of freedom, so we have 3, so I'll change that. And then we'll calculate. So there's that chi-square value, right? There's our test value, same as we computed longhand. And the next thing we get is the p-value, so 0.455. That's a really big p-value, right? That's much bigger than alpha, so that gives us the same exact decision. Okay, so let's do one more example. I'll just do this one on the calculator. I'm not going to do it by hand this time. So Pew Research Center stated the following percentages about U.S. Gen Xers' attitude towards religion: 53% very important, 25% somewhat important, and 22% not important at all. To see if the attitudes are similar, why don't you survey 100 Gen Xers, here's the years, and you find this. So these are what we observed. So I'm going to go ahead and put those in my observed so that I can stop looking at them. So I've got a table all set up. So this is what actually happened. So these are the observed. So 65 said very, 20 say somewhat, and 15 not important at all. Okay, guys, and you know me. Let's make sure those actually add up to 100 because that would be something I do. So 65 plus 20 plus 15. 65 plus 20 plus 15. 100. Oh, good. Okay, so now let's find our expected, right? Do they fit what the Pew Research Center says we should expect? So 53% of the 100. So it's nice that I did 100. You're welcome. So 53. 0.25 times 100, 25, and 22. So hypotheses. So chi-square equals 0. as expected. Chi-square greater than 0, different. If I would have given myself more room, I would have written more words. Please write more words. And then, let's see, alpha, 0.1, okay. Degrees of freedom. So I have 3 categories, so 3 minus 1 is 2. So I'm going to go back to my lists. I'll just use those same lists, clear them out, do it again. So observed into L1. I keep doing 4s for my L's today. Something's going on. So 65, 20, 15. So like, I'm going to say time-wise, it's about the same to do it by hand, especially with this few numbers, to do the test value formula. Right? It's about the same number of keystrokes or same amount of time, but think about how many arithmetic mistakes or calculator mistakes you could make with the other computation. That's kind of why I like this chi-square goodness of fit test. So now stat, test, chi-square goodness of fit, and since I use those two, the only thing, be sure to change your degrees of freedom to 2 now, and down to calculate, and my p-value is 0.05. My test value, that one on top, 5.944. Critical value, I don't have that. We can go look in just a second, but I know my decision. So my p-value, 0.05, is smaller than alpha. So we are going to, not there, down here, we're going to reject the null hypothesis. It is not true that it's expected. So there is enough evidence to support the claim, and I know there's not really a strong claim here, that Wenatchee's attitude about religion is different. Okay. I told you I'd show you the critical value. So 0.1, 2 degrees of freedom, so 4.605. And our test value, 5.94, so that's bigger, so it would go to the right. Okay, so that's how you do chi-square goodness of fit.